All right. First of all, welcome. I'm glad you're here. Ms. Luna had to be out this week at a training session, and she's asked if I could sit in today and Thursday, which I'm happy to do. Thank you for coming in for the class. Clearly, this is going to be online. I know that you're used to doing face-to-face now the last couple of weeks, but I have a class downtown not long after this class ends. So to obviate the need to make that drive, especially in downtown early morning traffic, we're going to be doing this today and Thursday online. The slides that I generate here will be forwarded to Ms. Luna for posting to Blackboard. Also, so that you're aware, this meeting is being recorded and in theory will be available through her Blackboard link in Panopto. So I am Dave. Hi, how you doing? How you doing? I've been teaching pre-cal a while, both here and at the high school and as dual credit. So any questions you have, I gladly would take. I ask only that you unmute and say, excuse me, hang on a second. Why did you just say that 2 times 3 is 5? All right. And one thing I have difficulty with is, hang on a second there, Dave. I don't get it. That's not a question, that's a statement. And all I can do is agree with you. All right, you don't get it. So please, when you pop in, ask a question, even if you're not quite sure what it is you're asking. Make sure you get it dealt with. Remember that you are the one person in the world right now that is advocating for you. Make sure you get an education. Make sure that you make me do my job to facilitate your getting an education. I'm glad you're here. All right, so chapter 3, inverse trigonometric function. And from now on, I'm not going to be writing out function. Fx is function. Inverse function undoes the original function and vice versa. The original function will undo whatever the inverse creates. That is that if I put a question into a function, I get an answer out. I take that answer, put it into the inverse function as its question, and what pops out the other end is the question that I originally asked the first function. So they undo one another. One of the things that facilitates this is that X and Y, or domain and range, exchange places. What was X is now Y. What was Y is now X. And this helps us to set up something called 1-to-1. A function must be 1-to-1 to have inverse. What that means, now not only does X have a limitation, it can only marry up to a single unique Y, but Y now can only link to that X. So it used to be that X could only have one Y, but Y could play the field. Look here at X squared in the bottom left. This is a poor drawing of X squared. I can't draw, by the way. Whatever I draw, I'll give you a name, and that's what that thing is. All right, I am drawing challenged. We see that it's a function by the red vertical line test, right? No problem, it's a function. But when I draw a horizontal line to check for 1-to-1, I fail because I touch the graphed thing more than one time. So in order to be 1-to-1, we now have to pass 2 tests. We must be pass the vertical line test for function and also the horizontal line test for 1-to-1. Now, we can sometimes do this. We can limit the domain of our function so that we create a one-to-one situation. And I did that here with x squared, but only allowing the input from 0 toward infinity. Well, when we do that, we only have this one arm, and it passes a vertical line test and a horizontal line test. So if we're only putting non-negative input to x squared, then we have a one-to-one and we have an inverse, which undoes it, and that is x squared. Any questions on what inverse is? Well, you're an easy group, aren't you? All right. Well, clearly, we are here to talk about things other than x squared. We're here to talk about trigonometry. So let's take a look at sine of theta. Now, we know that sine of theta is a repeating function. We know that it's passing up through origin. Well, if I could draw, it would be passing up through origin. Let me give it one more try. From its least y value to its greatest y value, where it turns around, goes back down through the y to its least value, back up again, and so forth. Now, clearly it's a function. It passes the vertical line test all day long, but fails the horizontal line test. It is not in its basic form, not one-to-one, because it fails the horizontal line test. So what we're going to do to have inverse function of sine, we limit the domain of sine. And looking at the y-axis, if I were to begin there, I'm going up. I have all of the possible positive responses until I get to 1. And then I begin to repeat all of those possible positive responses. So I'm up to pi over 2. I have no repetition. And if I look the other direction, if I go a negative angle, then I have all of the infinity of possible negative responses back to negative pi over 2. We may draw our answers to inverse sine of a value to quadrants 1 and 4 between negative pi over 2 and pi over 2. And this, of course, is the range. The domain for arcsine or sine inverse is the range of sine negative 1 to 1, also inclusive. So if we have a circle here, and that's, no, it's not too horrible a circle. We have.
Sir, I have a question.
Yeah.
Sorry. After it says domain for and then I can't read what it says. I'm so sorry. It says a something sign. I don't know if that meant like area sign, or I just can't. I'm sorry.
The right here?
No, further down at the very bottom, the last line says domain for. I just couldn't read that last sentence.
Domain for arcsine of A.
Okay, thank you so much.
And thank you for asking. So here we have all of the possible positive y values. Oops. And here we have all negative y values. All right, we don't use quadrants 2 nor 3 because those would be repeating either the possible or the positive or the negative values. So is it okay to move forward? So sine of theta, we're going to limit the domain to create 1-to-1. To negative pi over 2 to pi over 2. And we can go right up and touch, and that's inclusive. And the range, of course, hasn't changed. That's negative 1-to-1. Those are all the possible answers to the simple basic parent form of sine. So this is called sine inverse or arcsine of a value of A. And the domain is what the range is in its inverse, the original function, negative 1-to-1. That is, we're putting in a number between negative 1 and 1. And the range, the angle that we're pulling out, will fall between, including negative pi over 2 to pi over 2. So, as an example, if I asked you about the sine inverse of square roots of 3 over 2, sine, remember, is analogous to the y, right? It's so when we write the trig values, we write them like we do a coordinate. X, y is alphabetic, so is cosine sine. Sine is essentially y. And we have here 1/2 and square roots of 3 over 2. This is our x, this is our y. So the angle for which sine of theta equals square roots of 3 over 2 is pi over 3, or 60 degrees. All right. So when we're doing this, we're kind of playing Jeopardy, right? We're saying, well, the answer is square roots of 3 over 2. So what was the question? Well, the question was, what's the sign of pi over 3? Make sense? Everybody knows Jeopardy. Any questions so far?
Sir, when you said that the sign is y, which is pi over 3,
Well, pi over
are you,
3 is the angle.
I'm sorry, pi
The-
over 3
Is the
yeah,
angle.
the
The
60 degrees.
cosine, yep, the cosine of pi over 3 is 1/2, right? And the sine is square roots of 3 over 2. So the question I'm actually asking when I say, what is the arc sine of square roots of 3 over 2? I'm really asking, for what angle is the answer to sine equal to square roots of 3 over 2? And remember, I can only answer out of quadrant 1 and quadrant 4.
That makes more sense. Yes, I understand now. Thank you.
Bueno. Good on you for asking. Daily A for you. We good, guys? All right, let's look at another. So looking at this, we have pi over 4, which gives us square roots of 2 over 2 and square roots of 2 over 2. The value is positive. So the angle comes from quadrant 1 and at pi over 4, sine of theta is square roots of 2 over 2. So the arc sine of square roots of 2 over 2 is precisely pi over 4. That's the angle that if I said, what is the sine of pi over 4, you would say square roots of 2 over 2. What about the arc sine of negative 1/2? The value is negative, and y is negative in quadrant 4. So arc sine of a negative must be in quadrant 4, which we use negative theta to describe. So we would say sine of pi over 6 is 1/2, but we need -1/2. So we simply for arcsine and arctangent only, make the angle negative. All right, so instead of going in a normal counterclockwise manner, we're going to go the exact same distance, but we're going to go clockwise. And we would say -π/6. Now you're looking at this going, wait a minute now, last week, Ms. Luna told us that that was 11π/6. And you're right, it is. If you said 11π/6, you would be in exactly the correct place. But you would be getting there incorrectly. To say 11π/6 suggests that you went through quadrant 1 into quadrant 2, already a no-no because now you're repeating all those positive answers, into quadrant 3 and getting all your negative answers, and then repeating them in quadrant 4. So we're using two quadrants that are barred to us when doing arcsine. So arcsine and arctangent, or sine inverse, tangent inverse, this is very simple. We figure out what the angle would be in quadrant 1, and we simply put a negative sign in front of it. So the arcsine of -1/2 is -π/6. Not too horrible, right? Only a little bit horrible. Any questions on this? So if I'm asking you about the arcsine of a positive value, that angle must come out of quadrant 1. If I'm asking you about the arcsine of a negative value, that angle must come from quadrant 4. No questions? You're a happy group, aren't you? I'm jealous. All right. Cosine theta must also be limited, must also have a limited domain. Let's say that. Cosine, remember, starts at the top of its range, falls down through y on its way to the minimum of its range, and then turns around and comes back up and so forth, right? So clearly passes the vertical line test and proceeds then to fail the horizontal. Now, if I'm starting at the y-axis at 0, I've got all of the possible positive answers falling from 1 down to 0. Well, 0 is not positive, but you know what I mean. And then we have all of the possible negative answers. And we begin to repeat. So at pi, we stop. Cosine theta has a restricted domain of 0 less than or equal to theta less than or equal to pi. Range has not changed. It's still negative 1 to 1. So arc cosine of alpha has a domain of negative 1 to 1. We can put any value in between negative 1 and 1. And a range of possible answers between 0 and pi. Or quadrant 1 and 2. So positive in quadrant 1, negative in quadrant 2. And that's because cosine is analogous to our x. Cosine is analogous to our x. And so we have moving counterclockwise from the positive x-axis. We have all of the possible positive responses up to 1. And then we have all of the negative responses from 1 back down to 0. And the inputs are positive in quadrant 1 and negative in quadrant 2. Okay, so let's look at some examples. So the arc cosine, or the cosine inverse of square roots of 2 over 2 So what we're asking is, where in quadrant 1, because positive, right? Well, we know that that happens right there at pi over 4, 45 degrees, where we have the same value for cosine and for sine. So the arc cosine of positive square roots of 2 over 2 is pi over 4, or 45 degrees. Now what about cosine inverse of negative square roots of 2 over 2? A negative a value tells us the angle is in quadrant 2, where cosine theta is negative. And as it is the same value, same distance, so the arc cosine of negative square roots of 2 over 2 would be 3 pi over 4, because cosine of 3 pi over 4 is negative square roots of 2 over 2. So arcsine, arctangent are easy. You figure out whatever it is you need in quadrant 1 and simply make the angle negative. In quadrant, for arc cosine, cosine inverse, it's not quite as easy. It's not difficult, but we need to add whatever we have to add to get into quadrant 2, where cosine is negative. Go. Now, did she teach you guys to use your left hand as a memory aid?
No.
I'm going to guess by the silence. Okay. Then I don't want to mess things up. So you guys are memorizing each of the quadrants. Okay. I have a different approach. I don't want to mess you guys up. So if cosine of 2 pi over 3 is negative 1/2, then the arc cosine of -1/2 is 2 pi over 3. We are naming the angle that, when you take the cosine of it, creates the answer -1/2. What do you think? Extra stupid horrible? Nah. You guys good-ish? Any questions? All right. Now remember that tangent theta is the same as sine theta divided by cosine theta, y over x, and cannot exist where cosine of theta creates the answer 0, because that would be division by 0, and that's not allowed. Doesn't matter what math you're in. Yeah, I can't do it. We will sketch in cosine to draw our vertical asymptotes where cosine equals 0. So we're going to do this. Remember, we're laughing at my drawing. Okay, so everywhere that cosine touches 0, we have a vertical asymptote. This happens at pi over 2, 3 pi over 2, negative pi over 2, and negative 3 pi over 2, and forever and ever in both directions. Tangent then is this kind of lightning bolt sort of a shape, rising up out of negative infinity towards positive infinity, passing through origin. And it is here that we limit our domain because if we didn't, we would just have it repeated here, 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 right? So we only want one of them. Tangent theta limits domain to negative pi over 2 to pi over 2, just like sine, but can't be equal, right? Because those are vertical asymptotes. Range doesn't change. It's still negative infinity, infinity, which of course will never be equal to. Making arctangent or tangent inverse of a value has a domain of all real numbers, negative infinity, infinity, and a range from negative pi over 2 to pi over 2. So this is the extent of our possible answers. So, like arcsine, we are pulling from quadrants 1 and 4. You guys doing okay?
So basically, this is the reason why the graphs are shaped the way that they are when we're looking
Yeah.
at them graphically.
Yes. Did you talked about this, right? In chapter 2 about the graphing? For instance, secant, which is the reciprocal of cosine, right? So wherever cosine is 0, we draw a vertical asymptote, right? We sketch in cosine, and then everywhere cosine has a maximum, we can sketch in these kind of sort of parabolic shapes, right? So these red parabolic shapes, these are secant. So if you were graphing secant, you would erase everything else and just keep these upward and downward facing more or less parabolas. Yeah. Kind of a shortcut way to get an idea what your graph looks like. All right, so let's look at some examples. Oops, helps if I don't have erase on. There we go. Arctangent of -1. So it's perfectly okay for me to ask a positive or a negative anywhere, because the graph of tangent and arctangent have an unlimited, well, arctangent domain and unlimited range on tangent. So what we are really asking is, where is tangent of the angle equal to -1? Well, we're limited to quadrants 1 and 4. So here is 0. Here's tangent equals come on. In tangent, remember the tangent is sine over cosine. So at 0 radians, 0 degrees, we have a tangent equal to 0, because 0 over 1, it's kind of like saying there's no cake in the room, how much does everybody get, right? You can divide a number into 0, but you cannot divide a number by 0, because dividing is really just repeated subtraction, right? And if I'm trying to take nothing away from a thing, it's never going to get smaller, right? And so there's our answer. We can take it an undefined number of times. We can subtract and never ever change our value. Okay. So tangent at pi over 4 is equal square roots of 2 over 2, square roots of 2 over 2. So tangent is equal to 1. And then down here at negative pi over 4, we have tangent then equal to negative 1. So this tangent 1 comes up a lot. Okay, so you need to know that that's pi over 4 or negative pi over 4. We answered just like we answered for arc sine. All right. Are you comfortable with tangent's weird? Are you comfortable with tangent? You want to take a minute and talk about it? All right. I'm the teacher, so I'm going to make you talk about it. Okay, tangent theta is sine theta over cosine theta. Or on a unit circle, we can simply say y over x. Arc tangent of A is undoing of tangent. So we have 0 degrees, 0 radians here. Here we have pi over 6. Are you starting to get used to your radians? Yeah, we're going to be switching to nearly exclusively radians. So you want to get a handle on them. You want to be comfortable with them. Now we know that at 0, we have 1, 0 as our cosine sine. And then we have square roots of 3 over 2, 1/2. We have the pair. And we have 1/2 square roots of 3 over 2. And then we have 0, 1. So tangent of 0 is 0 over 1, which is 0. That's not a big deal, right? Tangent of pi over 6 being y over x is 1/2 over square roots of 3 over 2. Don't let that scare you. That's called a complex fraction. It just means we have a fraction that has a fraction in it. So what this is really saying is that we have 1/2 and we're dividing it by square roots of 3 over 2. which we change, right? We say that that's 1/2 times the reciprocal of the divisor. And we can see that the 2 goes away top to bottom, leaving us with 1 over the square root of 3. But being good algebra students and true, we know that we are not allowed to leave it that way. So we say 1 over the square root of 3 times the number 1, so that we can get rid of that radical in the denominator. The squaring of a square root releases the radicand. So we have 3 in the denominator and we have square roots of 3 in the numerator. So the tangent of pi over 6 is square roots of 3 over 3. Pi over 4, well, you know what? Clearly that's 1, right? Because anything divided precisely by itself is equal to 1. Pi over 3, well, we're just going to flip the numerator and denominator from pi over 6, and we're going to end up with simply the square root of 3. And it's here that we have a bit of a problem, right? The tangent of pi over 2 would be 1 over 0, which is division by 0, and that is undefined. Okay. So remember that in quadrant 1, everything is positive. Quadrant 2, only sine and its reciprocal cosecant. Quadrant 3, tangent and its reciprocal cotangent are positive. Everything else is negative. And in quadrant 4, we have cosine and its reciprocal secant positive. Everything else is negative. So we remember what's positive. All, only sine and its reciprocal, tangent and its reciprocal, cosine and its reciprocal. So we remember all students take calculus, right? Questions on tangent? So the tangent, tangent of 3 pi over 4, which is in quadrant 2, is exactly the same base number as in quadrant 1, but it's negative in quadrant 2. It'd be negative 1. In quadrant 3, it would be positive, and in quadrant 4, the tangent of the 7 pi over 4 is negative 1. Same base number. Okay. That's another reason to get used to these radian values. When we see the same denominator, we have the same base numbers. We just change the positives and negatives, the SIGN signs. You good-ish? I don't hear anybody crying, so okay. So this is a composition. I'm taking tangent of 3 pi over 4, and I'm making it the a value to take the arc tangent of. So first thing I want to do is I'm rewriting this as the arc tangent of the value a, where a is equal to tangent of theta, and that theta is 3 pi over 4. Whoops. 4 feet. There we go. So 3 pi over 4, we know that the denominator 4 has the same two numbers, cosine and sine, square roots of 2 over 2, square roots of 2 over 2. But in quadrant 2, it's a negative cosine and a positive sine. So tangent is -1 over here. Then the next thing we're going to do, now that we have an answer for what is the tangent of 3 pi over 4, we say, well, what is the arctangent of 3 pi, sorry, what is the arctangent of -1? Remember, we may only draw from quadrants 1 and 4. Quadrant 1, if A is positive. Quadrant 4, if A is negative. And so arctangent of the tangent of 3 pi over 4 is -pi over 4. 3 pi over 4 puts us in quadrant 2, but we're not allowed to draw our arctangent from there, right? We can only draw our arctangent from quadrant 4, -pi over 4. All right, how many of you brought your calculators? Let's do this. Tell me about the arctangent of -8.45. I'll put approximate here. Let's do this in degrees. Make sure your calculator is set to degrees. What'd you get, folks? Good. How about this one? You staring at your calculator going, what the heck did I do wrong? You didn't do anything wrong. Favorite algebra, well, trigonometry teacher trick question. Okay, don't get caught. All right, I wanted to open it up because I know the test is on your brain from last week. So is there anything you wanted to ask or needed to ask that you're just not sure what you were seeing? You're in good shape? You guys are quiet. All right, well, she spoke really, really well to you guys. She feels very strong. You guys are very, very strong. So I'm sure that I'm just telling you stuff you already know. Any questions about anything we've discussed today? So on Thursday, I'm going to go a little out of order. Normally, we would jump right into 3.3, which is equations, but I believe that the equations will make more sense if I draw a few pages from 3.4 first. All right, because we're going to be making use of some identities and understandings in the equations that it's helpful if you know what they are first. All right, so I am going to go a little bit to chapter 3.4, and then we'll cycle back into 3.3 to work on equations. You know where we're headed? You know what we've done today? Do I have any questions at all? All right. Don't tell Miss Luna I'll let you go a little early. Have a lovely day. If you have a question you did not want to ask in a more public manner, if you want to hang tight, I'll take any questions. You too, Charlotte. Thank you.
Thank you.
Danny, Destiny. Good heavens. Lexi, now you're all talking. Hey, Anna. All right. Christy, Ryan, Emily, Andrew, any questions? Anything you didn't want to ask quite so public?
No, sir. You have a good day.
You too. Take care. Going once. Going twice. Thank you again very much.